Everyone, welcome to your Play Pause It for the day. We are going to basically pick up where we left off in our notes and work through these problems together. So don't forget you can pause this recording at any time and always reach out if you have any questions at all. In the diagram. So here we have the measure of CD. And you might look at this and say, oh, it's 90 degrees because it's across from this 90. But remember, that only works if this vertex is on the center. And it's not on the center. So we can't use the central angle theorem. We have to use what we just learned. We have a chord BD intersecting another chord CE, so they bisect. So we know these pieces are all congruent. Not all, but you know what I mean. ED is congruent to CD, and the two pieces of that chord are also congruent. So if they're equal, then let's set them equal. 9x equals 80 minus x. And let's solve for x. So we're going to get x by itself on one side. So that's 10x equals 80. And then keep solving. We're going to divide by 10. So x equals 8. Once you find x, we can go ahead and plug it into these to find the solution. So 9 times 8 is 72 degrees. So CD is 72 degrees. And without even plugging in x here, we would know immediately that this is also 72 degrees because we know they're congruent. But you could plug it in, right? 80 minus 8 is 72. So DE is also 72 degrees. And then it wants to know the whole thing. So that would be 72 plus 72, 144. All right, our next theorem. Here it says in a circle, two chords are congruent if and only if they are equidistant from the center. Remember, equidistant means equal distance. It's a fun word, equidistant. So let's draw what that means. Here are our two chords, C to D and A to B. And we're going to show they're equidistant basically by marking how far away they are from the center. So I drew some lines from the center and I put tick marks on them to show that they're equal, which means the chords are equal. If you think about it, that makes so much sense because we know a circle is a collection of points that are equidistant from the center to the edge. So if this chord is going to be placed in the same position from the center to wherever, then of course it's going to be equidistant because it's kind of sitting right in that circle in the same spot, the same length. So if AB is 5 centimeters, so this whole thing from A to B is 5 centimeters, obviously CD is 5 centimeters. The chords are congruent. So a lot of these theorems are sort of, I don't want to say obvious because that's not a great term to ever use in math because I understand that things are not always obvious. But as you start to work with them, it's going to be like, oh yeah, this totally makes sense. Of course they're equal. So here's another one. In the diagram of circle C, QR is ST and 16. So they're telling you those are all equal. So we know the chords are equal. So this is sort of the converse of what we just learned. We're saying the chords are the same, so they are equidistant from the center. So we know UC and CV are also equal. So we can set 2x equal to 5x minus 9 to help us find CU. So I'll subtract 5 and then divide by negative 3. Get x equals 3, but let's plug that in. CU is 2x, so 2 times 3, so that is 6. It doesn't tell us what the units are, so I guess we can just write units. All right, one more example. It says to draw a circle with a chord that is 15 inches long and 8 inches from the center. So here's our chord AB, and we're going to label that as 15 inches long. And it is how far from the center? 8 inches from the center. Draw a radius so that forms a right triangle. So remember, a radius is from the center to any edge. So here, let me get a different color. We could certainly do this center to this edge, or you could have done the other one, right? 0 to B. I'm sorry, O to B. How could you find the length of the radius? Well, hopefully you're kind of seeing now that we have a triangle inside of this circle. And so we know that that's a right angle. So anytime you see a right angle in a triangle, we can use the Pythagorean Theorem. So because we know that the distance here cuts this into 2 equal parts, we know this is 7.5. So we could do 8 squared plus 7.5 squared equals, we don't know. Let's call this x. And we can solve for that radius, or that hypotenuse of that right triangle. So 64 plus, what's 7.5 squared? I don't know. 5 times 7.5, 56.25. Plus 64 is 120.25. And then we're going to take the square root of both sides, right, to get rid of that squared. There we go. 10.9658. All right. Inches. It is plus or minus, but remember we're talking about length here. So we're really only going to take the positive value. Let's just say 9.7. All right, let's talk about tangent lines. Oh my gosh, it's so funny. I love this meme every year. It's so good. Hopefully you're laughing or rolling your eyes. Either way, I'm fine with that. As long as it got your attention a little bit. All right, so let's talk about a tangent line. A tangent line, it's just a line, and it's a line that touches the circle at exactly one point. So it's a line that touches the circle at exactly one point. So let's draw a tangent line. I'm going to get an actual line so I can make it look pretty, hopefully. Let's see here. Oh, look, okay. I didn't think it was going to let me move the line. I'm going to put it here. There's our tangent line. It touches the circle at exactly one point. And it might look like more than one point, but that's just because it's really close. But it's really only intersecting that circle at one point right there. If you zoomed in really close, you would see. And that point has the special name. It's called the point of tangency. So this is where the tangent line touches the circle. The last sort of word on here is secant. So a secant is a line that intersects 2 or more points on a circle. It intersects 2 or more points on a circle. So a secant line is really similar to a chord, except it goes through the circle. Remember, the chord touched each edge, so a secant goes through the circle at 2 points. There's an example of a secant. See, it's going 2 or more, in this case 2. A third point might be, if there was something in the interior. So as long as it cuts through the edge of that circle, it's considered a secant. So I'm sure you're sort of anticipating that now that we have definitions, we're going to get some working theorems, right? So here's our first one. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the edge. Or also, you could call this the point of tangency. So here's sort of our diagram on the left. AC is the tangent line, and in the point of tangency is B. So any tangent line to a circle is perpendicular to the radius, like automatically. So we drew a radius dB, and we noted it was perpendicular by saying that it forms a right angle there. So because of that, right angles are super special, right? Because we're allowed to form triangles and use the Pythagorean theorem. So if they wanted us to find AC, all we would have to do is do 3 squared plus 4 squared. And this is a special triangle, so you may have already figured it out. But this is 25 equals C squared. So C is 5, which I was calling this C. Little c. 3, 4, 5, right triangle. So let's try another one. We have our tangent line here. It's where the x is. And there's our point of tangency. So we know that we can form a right triangle with the radius. So let's set this up. Here's the hypotenuse because it's across from that right angle. So the whole thing, remember, is 18 plus 9, which is 27. So let's find x. So we know we're going to set it up x squared plus what? This is the other length of that triangle. How can we figure this length out? Well, look, it's a radius, right? From the center to the edge. What's this? This is also a radius from the center to the edge. So these are both 9. We use that clue in the picture to help us there. And 27 always goes, or the hypotenuse always goes on the right-hand side. So we're going to have x squared plus 81 equals, I have no idea what 27 squared is. You guys, that's a big number. 729. Alrighty. So now let's keep solving for x. All right, let's go to our calculator. 729 minus 81 is 648. And now the square root of both sides. So let's see. Square root of 648 is, we'll say 25.5. That sounds good. Didn't tell us how to round. So we'll just round it there. Units. Theorem number 2 with tangents and secants. This one cracks me up. It looks like a party hat. So tangent segments that form a common external point are congruent. So we have 2 tangent segments going on here. CB, here's the point of tangency, and AB, here's the point of tangency. And they form this common external point. So they meet at an external point. So you might guess it. I mean, it makes sense, right, that they would be congruent. So tangent segments that form a common external point are congruent. So I marked those congruent. So now let's find the value of CE and AE. This might look confusing. It does to me when I first see a diagram like this, but let's just work ourselves through the picture and try to isolate some things. So here are two tangent segments, FE and DE, and they form that common point at E, so we know these are equal. Same thing up here, AB and AF. They're common tangent. So if this is 1.8, this is 1.8. This is 2.4, this is 2.4. Now that we have everything labeled, let's find what they want. So CE is this one. So that's just 7 plus 2.4. That's 9.4. And then let's see, AE is the other side. (1.8 plus 7). So that's 8.8. All right, you guys, look, we are almost done. One more slide. I kept it almost under 30. Here's another example. We're saying that points A, E, and D are tangent to circle O. So that tells us that we have some tangent lines going on. Find BC. So that's this whole length. So let's use what we have. So AB is 4. That means BE is 4. And similarly, this is 2, so EC is 2. The whole thing is 6. That's it. I hope you all have a great rest of your week, and I will see you guys next week. Bye, everybody.